Good morning, everyone. And thank you for joining us for this session, Uber's Innovation in OpenSearch for a Cloud-Native Future. And I'm Pallavi Priyadarshini. I lead search, security, and releases at the OpenSearch project. And I'm also a member of the Technical Steering Committee. And I'm thrilled to introduce Yupeng Fu here. He leads search and real-time data platform at Uber. And Yupeng is a very valued member of the OpenSearch Technical Steering Committee as well. And I'm honored to share the stage with Yupeng and rest of his colleagues who are sitting in the audience. So Uber is a premier member of the OpenSearch Software Foundation and has been significantly contributing towards shaping OpenSearch towards a cloud-native architecture, and we'll tell you how. So I'll briefly go through the journey of OpenSearch with highlights on what is the current architecture and how the new architecture is evolving in open source. And then Yupeng will come in with the unique use cases at Uber that make cloud-native architecture essential, and then what Uber is doing about it in open source. So quick recap. Most of us are already aware, but OpenSearch is a community-driven, trusted, open source platform that powers search, analytics, observability, and much more. And it's an integrated vector database. At the heart of it, OpenSearch is a search engine built on Apache Lucene. And it was transferred to the Linux Foundation in September of 2024. And it's probably one of the best things that has happened to the project. It was done with the intention of building a vendor-neutral community. So with the transfer to the Linux Foundation, the OpenSearch Software Foundation was formed, and we have all these members in the OpenSearch Software Foundation, and Uber is a premier member. So the neutral foundation allowed the community to expand with more external contributors. And what is most exciting is this community maintains a public roadmap with the innovations in the key theme areas that we want to focus on. And the Technical Steering Committee is comprised of a diverse set of members from these companies that help shape the roadmap and also establish some technical governance processes. So our partners, such as Uber, who already run at scale, they are pushing the boundaries of scale, performance, cost, operational simplicity in open source, right? And that's why we are working together towards a cloud-native architecture. So this is kind of an overview of what OpenSearch in open source looks like today, right? There are data nodes which serve multiple roles. Each data node can be a reader or a writer. And metadata or cluster state is really a monolith today, and it needs to be propagated to all the nodes. And because of this architecture, where the data nodes have shared responsibility and cluster state is very big, maintaining or running large-scale deployments become challenging, and scaling on demand is also not easy, right? So in open source, it is going to a cloud-native architecture has been a journey we have been on, and a very important part of that journey was our move to the remote object store architecture, which we already did, right? So in the indexing flow, the segments get uploaded to the remote object store today in open source. However, on the search side of things, the data is getting served still from the local disks, right? So where we are headed towards, this is the architecture that's evolving. And in this architecture, on the ingest side, the data goes to an event stream, and dedicated writers are pulling data from the event stream and upload to a remote store. And on the search side, again, dedicated searchers are pulling data on demand from the remote store to serve the results. And the cluster state, or the metadata, is also in remote store, which already exists today. But what we are working on is breaking up the cluster state into smaller components so that each microservice only downloads what it needs. So what are some of the key areas in open source where we are seeing a lot of work towards this cloud-native architecture? One, obviously, the storage compute separation. So as I mentioned, we are moving towards a true remote store architecture. And today, it is done for durability. But as we advance in this journey of re-architecting, we are separating out components based on this remote store architecture. And the separation of components allows independent scaling. You can put resources where it's needed. For example, if you're a logs customer, you can put more resources on the ingestion side of things. It also improves resiliency, because with remote store, your node restarts, your node replacement become much more robust. So as I mentioned, the cluster state is already moved to the remote store, but we have work in flight that is going on to break it up into separate logical and physical components. And that's cluster state is very important to maintain the health of the overall deployment, right? Reader-writer separation. So because we have the remote store architecture, we could build separation of readers and writers. And this allows that the searchers and the writers don't interfere with each other and can be scaled independently. So in a real use case, you don't want your search latencies to be impacted because you're ingesting data, or vice versa, right? So we have the reader-writer separation now. Then obviously, as we are breaking the code up into different components or microservices, we also need to make sure that the messaging protocol is efficient for different components to communicate. So OpenSearch is taking steps towards a more performant alternative to the existing REST APIs. And we are rolling out experimental protobuf with gRPC in OpenSearch 3.0. So unlike traditional REST APIs, which uses JSON, gRPC and protobuf, as its message format, makes data transmission more efficient as you're moving around lots of data, right? So the last bit is the pull-based indexing, where we are able to gracefully handle spikes in ingestion. You can prioritize your ingestion queues and do much better workload management with the pull-based ingestion. So I'm very happy because we've been on this journey, and these were the few missing pieces we had in our move towards the cloud-native architecture, and there is active work going on. And all three that you see on screen right now, the reader-writer separation, the gRPC protobuf, we've also added some streaming support, pull-based indexing. They're all part of OpenSearch 3.0, which is going to roll out as early as next week, right? So OpenSearch 3.0 is a very important step in our journey towards a cloud-native architecture, and we will continue expanding on it in the 3.x line. So with that, I turn it over to Yupeng to go through the Uber requirements and their contributions. Thank you.
Thank you, Pallavi.
Yeah.
Good morning, everyone. We're excited to be here and to share our joint work with Amazon and the community on changing OpenSearch project itself to become more cloud native. So first of all, our use cases at Uber, a couple of days ago, when I first arrived here, I was amazed to see, there are Uber's cars on the street. There are bags carrying Uber Eats, bags and baskets, same as what I have saw in San Francisco, where I'm from. So today, Uber is already a global company, and we operate in many cities. And we have over 1 million restaurants on Uber Eats today. And you can see for the Uber Eats, search actually plays a very critical role in the application. It's one of the core functionality of this application to our customers. The reason is that it needs to capture the user intention. And our customers have various intentions on what they want to have. So this is very interesting problem, especially very interesting search problem. On the other side, all merchants or restaurants on the market, they provide a lot of offerings. Healthy food, vegan food, there are different choices to our eaters. And therefore, this becomes a complex decision-making problem to our customers. And to make our customer experience better, we, as infra team, also application team, we do a lot of additional work trying to design the application in a certain way that with the least keystrokes, the customers can identify what they are interested in. So my next slide will talk about some interesting problems we see from the Uber Eats application. The maps, which is also at the heart of the application of the Uber app. So both for the delivery business, which is Uber Eats, and also for the Uber rides, maps is a key part of this application, which is also a very interesting search problem. That if you use Uber apps, that you will see a screen like this, and you see there's some predefined options, like where you want to go, some choices from your search history or from your profile. But in addition to that, just with a few types characters, we're trying to get the location you are interested in. This is actually a very complex problem, and we work with our maps team refining our search solution. And we're taking cutting-edge technologies like semantic search, contextual search in the search solution design. For example, for the same queries, say hot food, we may give you different choices or restaurant locations depending on the time of day. In the morning, you may want to go to some coffee place, but in the evening, we'll return you more restaurant that is open. And similarly, for the contextual information on the maps, that if you say in San Francisco, if you type Chase, we'll probably return you the Chase Center, which is a famous Warriors play center. But if in other places on the country, we probably return you the Chase Bank that close to you, especially during the business hours. And next is our rides business. This is also very challenging and perhaps the most important search problem that over our platform. So essentially, Uber is trying to solve a matching problem for our riders and riders. So drivers will, they are moving around in a car while, our riders, you take up the app, you click a button, and trying to find matching drivers with you. And the key challenging problem for this search is that the drivers can move around and they are moving fast. And therefore, the freshness here plays a very important role. In just a few 100 milliseconds, we want to index all the locations and the latest locations of the drivers, and trying to find the most the best the matching to our riders. And the rules can be complicated. There can be regulation, compliance requirements, could be preference for people who, for example, prefer more business and comfort kind of ride. So we need to also serve this query very fast at fingertips that we can return the results to you because we know our riders are waiting for the car, right? So all of this presents unique challenges to our platform. And last but not least, right, so in the GenAI era, we're also heavily adopting the LLM and the GenAI solutions in our applications, in our solutions. One interesting example here is that if you have tried customer support lots of customer support now is through the chat, like from the bots. And that can actually improve a lot of both the customer experience because there's always someone there, like even though it's a bot, to provide the answer. But also more importantly, that is play like big cost efficiency like win for the company. So here are the demands. I'll quickly show you our search platform. Our platform also has been in the transition mode. And this talk is mainly talk about like our journey and our ongoing work and also our future. So in the past, we have been building an in-house solution that also built on top of Lucene. And it has a Lambda architecture because in my previous slide, we showed like real-time data is very important for us. And freshness plays a very critical role. And therefore, like we care a lot about like the most recent data. And that's why the streaming like ingestion is very important. And we also have like historical like data, like for example, the restaurants, the catalogs, and also the geo-sharding. If you look at like Uber, where like our data is highly like geo-based, like restaurant in a city, and through like geo-sharding, we can make much more optimizations and a certain intelligence to return the results faster in a better quality. And lastly, due to the large-scale data that we have, like we optimize a lot on the index layout and also query operators so that we can return like query fast. And we can do the certain ranking in the offline. For example, in the restaurant like data, we'll try to capture the popularity, how popular these dishes are, and then pre-rank them so that we can do a certain early termination during the query time. Let's do like one quick case study, let's say our delivery. So there are two ways to order things on Uber Eats app. One is through feed. We open up the app, you can browse, you can see the feed, or you can go to like a text box and search things like you like. But behind the scene, both of these actually go through the search platform and we capture as a search query. And there are a lot of like query understanding, query refinement as part of the pipeline, and to inject additional like signals. For example, we collect the time of day, the location, the user profiles. So we make the query, we enrich the query, and then we try to provide like better results. But just in a nutshell, the delivery data can easily captured in this way. It's a very classic parent-child relationship. So at top, we have a lot of like stores. And in each store, we have many items. Some store could be like very small. For example, we have like local like a restaurant. But we can also have like a huge store, like for example, Costco, like a Target, a chain store that have millions of items. And the key challenge here, or say like through the query that we show, which is essentially you can capture as a local join query that the user provides certain conditions. For example, they like the items to be like milk. And we capture the location of the user, let's say in Amsterdam. And then we try to find the relevant items from the stores, and then we group by the stores and we return. So here the grouping of the stores is very important because we care about like diversity of the results we return. We don't want to be like, okay, we will search a burger and then your top 10 results are all from McDonald's, right? That hurts the diversity. We want to have certain balance. That's why for each store, we want to put a cap on the maximum number of right items that return, but we also try to return as many stores as possible. And then we'll pass it to we call this like second pass ranker, which is also a machine learning model trying to better rank them. So why this like a challenging like problem? So as I mentioned, like we have a lot of like catalogs, and also for the better search experience, we want to provide the search result from different like categories. Like could be like restaurants, could be like grocery store, could be like alcohol, and those kind of like. And therefore we have a huge like catalog. And for people who are familiar with Lucene, you can see Lucene provides two types of join operators by default. One is like query time, like join, which is essentially that, like you have a parent key, and then you're trying to use parent key to retrieve the child and the children, and then you do some like join on the fly at runtime. Another way is called like block join, which is you pre-sort all the documents, and then it can be more efficient because you put certain complexity to the ingestion time. However, for the block join, like in Lucene, that you have to ingest all the documents of this entire block at one time. And you cannot make like incremental changes. But here, for our use cases, that the changes can happen like constantly. Like store can be open, closed, item can be added, removed, or the content can be altered. So the key challenge in this particular use case is actually how to run the join query efficiently. So then we build like something like hybrid. We call this like efficient parent-child join operator. So the key idea is that we will always assume the index has the sorted like layout, in the sense that like we'll first have like a parent, which is like store, and followed by all the items, and then next store, and then all the items. On top of that, we also do additional grouping, like we group all the stores in the same city together, because that makes sense for the efficient like query. And on the query operator side, you can see on the right side of the screen that we keep multiple pointers, like pointer to all the parents and pointer to all the eligible parent like iterator. Also, why there's eligible parent operator, because it's also possible for people to put a condition on the stores. Let's say I want like the store to serve only like vegan food, right? So that's called a condition, right? And similarly, we have a pointer or eligible child iterators. Like I only care about like items that are relevant to milk. So with this like efficient like operator, we should be able to quickly iterate the entire index and then return the results efficiently. But you can see here is not just about innovation about like one query operator. The complexity behind it is actually how to maintain this index order. So as I mentioned, so the index should also always be in this kind of like sequence or this order. But Lucene itself does not provide this kind of like guarantee, meaning each time you add you have additions or deletions or updates coming in, you have to trigger like sort again. And this sort is very expensive. And so expensive that it will impact the query latency, and it will be kind of like stop the world on those the nodes trying to do the data ingestion or doing the sort. So that's why this requires a reader-writer separation at architecture level. And that's inspires the team to build certain innovations into the system so that we can operate in this mode. And earlier, as Pallavi said, so that's where the cloud-native architecture coming in to trying to provide this kind of platform support to this kind of queries and paradigms. So this is high level what our architecture is like. So we ingest all the data from Kafka, and we have a role called ingesters. This is kind of the writer component. If you look at the CPU utilization of this writer role, it's almost always over 90%. It's doing a lot of heavy computational work, busy ingesting, sorting, and reordering the documents and generate the index. And the index, once generated, you upload to a remote storage. And it could be S3 or it could be HDFS. And we download this to the searcher node. Searcher node is critical for serving, and we care about its reliability. We care about its latency, and we try to keep the serialization low, below 30%, so that we do not see spikes on the queries. And also a good thing about this is that we'll be able to make the searcher scaling like more horizontally, because our query can be seasonal, right? So during the day and night, the traffic pattern will change. So having more elasticity on the searcher side, we'll be able to scale the searcher based on the QPS, and without worrying about the cost efficiency, those kind of like challenges. And we also have like we call this like offline build component, which is useful for Bootstrap, like backfill, like data correction. So this is through like Spark job. So Spark can read from our data source like Hive, and then directly generate the index, and then place it, and can directly upload to the remote storage. So that's taking a different like route in the Lambda architecture. So like then what about like OpenSearch? Like since we already have a solution in-house, why we want to work with community? So this is like last year we started like we call this like product sunrise. The key idea is we want to collaborate with the open source ecosystem to drive sustainability and foster innovation. So there's a famous proverb saying, if you want to run fast, run alone. But if you want to run far, you run with a group. Here, we want to run with a group, with a community, with this open source project. So we can take not only our innovation into this community, but we can also benefit and leverage other contributions from other companies in the same community. So you can see on the challenge side that search is very demanding. And we get requirements from our customer teams, product teams. They want to try new features, right? So they want to have like cutting edge, like vector search, like solutions. And the other day, there's something new in the Gen AI like landscape. So there's like a lot of driving force from our customer side. And also from the platform side, there are also a lot of demands on better tooling, like better like visualization, observability. And with a small team in a company, we're not able to build all of this by ourselves. We need a community, like we need a mature like project like OpenSearch that has a rich ecosystem, lots of plugins, very nice like dashboard. So we get like the best for both. So we are able to contribute our innovation to this project. In the meantime, like we will embrace like the other good features from the ecosystem. That's how like last year, like we joined the OpenSearch Foundation, especially partner with like AWS, trying to reshape the roadmap of this project. And in a few examples, next slides to show some work that we have done, also we are actively doing. One interesting feature is this pull-based ingestion. So, for a company like Uber, almost all the ingestion that we have are from like Kafka. So one good reason in that is that this can smooth the ingestion specs. Or in other words, this separate concerns of the producers and the consumers. In this case, OpenSearch is a consumer, right? It will try to read data. But when there are like a lot of heavy load coming in, it becomes like producers like problem, right? They need to see the throttling error. They need to pace their side accordingly. But this kind of like problem is already solved by Kafka. And with this, we can also being able to leverage other features of Kafka, which is they have an offset concept. So we can always like replay from the history because Kafka itself solved the durability problem of the data flow. Another important feature that we leverage from this pattern is like we have a all-active multi-region setup. So cross-cluster replication is a hard problem. I don't think it's fully solved yet in the OpenSearch ecosystem yet. But we solve this through the pull-based ingestion inside Uber because we use Kafka to do the replication. So each producer will just produce data to the regional cluster, and we have a cross-region replication to the aggregated Kafka, which has a global view. And then each OpenSearch cluster just need to read from this aggregated Kafka without worrying about data synchronization, those kind of like issues. So That's how we delegate like a very hard problem to a component that's already solved this problem. And in fact, this Kafka like aggregation is commonly used for other technologies at Uber as well, like for streaming processing databases. So we already have like very solid foundation like for the all active like design setup. So this is the architecture of pool-based ingestion that I don't want to dive into the details of this. There's like a design RFC linked at the bottom that describes how we build this feature. But I want to show how you can use this because it's already available in OpenSearch like 3.0 that is upcoming. So in the settings, you can create like a new special ingestion source. You can say the type is Kafka, and then you can configure how you want this initial offsite to be created, which is quite standard, like if you are familiar with like Kafka concepts. And also we build certain features like you can pause ingestion, you can resume, so there'll be more like detailed information you can find on the user documentation, which is included in the 3.0 release. And this upcoming feature we're thinking about, we're trying to add, which is this priority-based ingestion that built on top of the streaming ingestion to allow different priorities to the stream. So commonly in the push-based way, which is RPC way, that a challenge like how to differentiate the different RED API and what's the purpose behind it. Because there could be like critical like changes that we want to prioritize, but there's also could be like less important like background like ingestion. So the priority-based ingestion has a very elegant solution to this kind of like problem. gRPC protobuf is another important contribution that we made. So, like the modern architecture of systems, that gRPC is kind of the norm. In fact, at Uber, all our microservices communicate through gRPC and the protobuf. And we did observe like good efficiency, like in our experiments on this, we saw 20% faster query than the RPC and JSON way. So this feature was already like made in, and then you can check our like the latest like user guide on how to leverage this feature. And our contribution do not stop here. There's actually more upcoming work. They are actively working with this community. So one like major issue we recently like opened is this like cloud native OpenSearch architecture idea that will try to extract the metadata into external like storage like etcd so that we can make the system more modularized. And we can enable additional like better isolation between different components and then come with like good benefits like static routing, like leaderless like design. And along others, we're also trying to contribute the aforementioned like features I show in the slides into the OpenSearch. So I expect like in the next 6 months and 1 year, we're able to converge like our internal like innovations in this project. So that's it. Yeah, thank you everyone. And any questions?
Any questions? We have a couple of minutes.
Yeah, I have one. Over here. Yeah, so you were talking about the priority-based Kafka topics for ingesting. And earlier you had talked about how later data is more important than older data. Are those priorities able to be adjusted dynamically based off time? Do you have any solutions for that?
So yeah, the priority-based ingestion is trying to differentiate like different like sources. Like for example, in our catalog, we also like label and mark the priority of the places. For example, the restaurants or grocery store that have much higher like revenue impact, we place this as critical stores. And also we have like the scenarios like when you do like a backfill, right? So we don't backfill like a lot of data, but we do not want this like backfill stream that can congest the normal stream or updates from those like critical stores. So that's why we want like the priority-based like ingestion to solve this problem. But to your question about like contention between different updates, we also have the versioning concept, which is we use the existing like version like in OpenSearch, and you can also customize this through like a timestamp to decide like which one you should win if there are like any conflicts, if that's a question.
Yeah, I got thanks for the talk. I got a question, I guess, more for towards Amazon. I think it's very good that you're putting the foundation on splitting the writer and the reader and to improve the ingestion pipeline for OpenSearch. I was wondering, this work on supporting this kind of streams, will you support other kind of products doing the same? For instance, RabbitMQ streams or similar messaging, or maybe not messaging, but event stream products?
Yeah, I think that's a good question. And the way we are building out the components doesn't preclude integration with other stream products, right? So there's nothing in our architecture that will prevent, any other stream product. In fact, I would take this opportunity to invite you, just open a RFC. I mean, the kind of uptake we are seeing, someone opens an RFC, people get along. So that's how the community innovates and we get more going. So, I mean, if you need help, how to open, etc., like our architecture is very extensible and we allow different integrations. And even for the event stream, we are very open, right?
I think we have time for one last question.
Great talk, by the way. This is pretty much a question for Yupeng on how Uber implemented things. Because I noticed that you implemented Kafka for a lot of the data ingestion, but you're also using gRPC and protobuf, and there's quite a bit of like feature overlap there. So I was kind of curious as to how and why not use one or the other.
Yeah, thanks for the question. So the gRPC and Kafka, they are complementary to each other. So on the serving on the read side, it's primarily like the gRPC like based. And on the write side, the traffic that we want to go through like Kafka for better like durability, especially for use cases that care about like no data loss, right? So that's in fact like with the streaming ingestion or pool-based ingestion, we're able to achieve exactly once ingestion semantics, which is usually a very hard problem, like in the streaming processing case. So that's why, this on the right path, we want to use Kafka.
All right, terrific. Thank you very much. Another round of applause. Thank you very much.